His research interests are experimental quantum optics, quantum sensing, quantum enhanced imaging, quantum plasmonic sensors, bright squeeze states, electromagnetically induced transparency, orbital angular momentum of light, among many others. So today he's going to speak about encoding information in spatial correlations of bright entangled light beams. Dr. Ashok Kumar, the floor is yours.
Yeah. Thank you, Dr. Joy. Yes.
Yeah. And you may share your slide and start.
Yeah, I will do it. Can you see my slide?
Yes, it's visible. Maybe you can make it full screen.
Okay. Yeah, is it fine?
Yeah. Yeah.
Okay, thank you. I would like to thank the organizers for inviting me here. So what I'll be talking today, I'll be talking about, the title I kept like encoding information in spatial correlation of bright entangled beams. But I would like to emphasize the fact that my talk won't be covering only this specific aspects. So what I would like to give you, because I noticed that there are a lot of students here. So what I want to give an overview of spatial quantum correlations. And then at the end, I would like to talk about how we use these spatial quantum correlations for information encoding actually. So to start with, so I will begin with a motivation that why we are interested in spatial quantum correlation actually. So of course they have twofold advantages. One is in a technological point of view, they are applicable in many of the quantum technologies. For example, they are useful in quantum imaging, quantum sensing, quantum cryptography, and many more. And on the other hand, for fundamental point of view, they provide a nice test ground for entanglement testing or Einstein-Podolsky-Rosen paradox actually. So we can do fundamental science as well as quantum technology with those spatial quantum correlations. Moreover, if you are interested to know more about it, I would like to flash 3 review articles over in the difference appeared in the difference of 10 years. This is 99, this is 2010, and this is 2020. You can look at how over the time this research in this direction has progressed. So with this motivation, I would like to tell you what is the outline of my talk. So I'll be talking about, basically first I'll be introducing what do we mean by spatial quantum correlations. And then I'll talk about some of the spatial quantum correlation studies that has been done in this parametric ground conversion. And of course, I'll talk about some applications and limitations. And then finally, I'll come to the bright entangled light beams that I do work on it. And then basically I will talk about how do we generate those beams, and then how do we study the spatial quantum correlations in those beams, and then finally how we can do fundamental science as well as technological aspects with those beams. So I will cover with this motivation my talk. So to start now, coming to the quantum correlations actually. So of course, I said spatial quantum correlation, that means there has to be temporal also actually. So what do we mean by temporal correlation? If you look at most of the experimental quantum optics or quantum optical experiments, so what these experiments they deal with the temporal arrival of photons actually. What does it mean? It means that let's say you have a pair of photons. You have a source that creates a pair of photons, and then you detect these photons with detectors, let's say single photon detectors. Then what you are basically interested in those studies, you are interested in the arrival time of the photon over time actually. Basically, you will get a time series data, how photons are arriving at different time, and then what are their correlations over the time actually. So that's kind of study will give you kind of temporal correlation. On the other hand, the spatial quantum correlation, we don't care about how the photons are arriving over different times. What we do care about, we care about how the photons are arriving on a transverse plane, which is perpendicular to the direction of propagation. propagation. Let's say I have a twin beams or twin photons which are emitting. If I look at a transverse plane or perpendicular to the propagation direction, how the distribution of the photons in that transverse plane actually. So I'm interested in that actually. That's what in this kind of distribution, how their correlations are distributed. This kind of correlation will give me spatial information or a spatial correlation. So we want to study or we want to use this kind of correlations. Now, the important point is, of course, I have introduced the spatial quantum correlations. So now important point is, how do we generate those pair of photons actually? Of course, there are many techniques. And then, of course, the most prominent technique that we use by the nonlinear optical interaction actually. So you know that when you shine a laser or electric light to a medium, then you polarize your medium actually. Basically, the polarization induced in a medium can depend on the first or higher power of your fields also. So see what these higher power you see here, these higher powers are responsible for creation of pair of photons actually. And then, you know, the most conventionally used methods for creating pair of photon, which are based on this QIQT and QIQT3, they are known as spontaneous parametric gun conversion or Fourier mixing. So if you look at, you know, if you look at the spontaneous parametric gun conversion, I would say more than 99 or 95% people working in the experimental quantum optics, they deal with this kind of system actually. In that system, what we do, we basically, this is a 3-photon process. You interact a strong laser beam with a nonlinear optical crystal, and you create a pair of photons actually. And since, of course, this creation has to conserve the conservation laws of nature, so they have to conserve the energy conservation, they have to conserve the momentum conservation. Now coming to the spatial quantum correlation properties of those beams. So where do they appear, or how do I perceive spatial quantum correlation in this kind of experiments? So if you see here, then you know that you shine laser beam, you create a pair of photon. And basically you create pair of photon at one single point. You know, at one point, a photon is created into two actually. So basically the pairs that you have created, they have a common birth zone actually. This common birth zone gives position correlation to those photons. On the other hand, if you look at how these photons will propagate over the longer distance, that will be covered by this momentum conservation. You know that the total momentum of this one has to be equal to sum of these two actually. So that decides which direction they will go. Basically, that momentum conservation gives the momentum correlation to those photons actually. Now coming to you know, this is kind of fundamentally how position and momentum correlations are coming to these photons. But now in lab, being an experimentalist, I want to check that in the lab. So how do we check that these position correlation and momentum correlation? And for that, you can use simple optical system. Basically, to look at the position correlation, you can use an imaging system that images the birth zone of photon to your detection plane. That's how you can get the position correlation information. As I said, the position correlation is because of the common birth zone. Basically, effectively, you are imaging the birth zone to your detection plane and then looking at the position correlations. On the other hand, momentum correlations can be mapped to your detection plane by using Fourier lenses. As you know that, you know, the lens has a very important properties that if you put a lens into F to F configuration, it gives the Fourier transform of whatever is input plane at your output plane, at your far field or Fourier plane. That's how you can convert this position momentum or position correlations to the momentum correlation, or that's how you can get the momentum correlation information. So that's how you can obtain position and momentum correlation at your detection plane. Now, having said that, as I said, these kind of spatial quantum correlations has a lot of significance in the fundamental science. For example, to study or to look at the Einstein-Podolsky-Rosen paradox. So what it is, or how it is useful, how this spatial quantum correlation will be useful, I will be highlighting that in a couple of slides. So as you, by now, you must be aware of that, in 1935, Einstein, Podolsky, and Rosen wrote one of the most influential or controversial paper of 20th century, actually. Basically, they question about the validity of quantum mechanics, actually. What their experiments still, basically, it was a thought experiment. In that thought experiment, what they considered a pair of particles which are correlated in, which has a perfect correlations in their positions and momentum, and then I have a pair of particles which are perfectly correlated in their position and momentum, and I keep them like space-like separated. Space-like separated means if you want to have a communication, you have to have instant communication, you have to have a speed greater than speed of light, actually. So what it was, if you do the quantum mechanical calculation for this kind of scenario, what appears that, what they found that, it appears that this kind of scenario seems to violate the Heisenberg uncertainty principle, which is basically EPR paradox. So how it appears, I will tell you that. So in principle, actually, if I write the mathematically, it's just simple quantum mechanics. If I write the state that EPR thought, if you write that state in the position basis, let's say A and B are my two particles, and then I can write that state which has perfect correlation in their position and momentum like this. That means if I do the measurement on position of particle A, let's say I get X prime measurement, then definitely I can predict the position of particle B as X prime. The same state I can write in the momentum basis, just the basis transformation of basic quantum mechanics. Then it turns out that if you write the same state in the momentum basis, also it turns out that there's a perfect correlation in the momentum of those particles, actually. So that means that means by doing the measurement on particle A, I can infer the position of the particle B, which is space-like separated. And the same thing, by making the measurement on momentum of particle B, I can infer with certainty what is the momentum of particle B. So since what Einstein EPR thought that there is no instant communication should happen, so what they thought that it appears that the particle B, which is space-like separated, is having already precise position and momentum, actually, which is against the spirit of Heisenberg uncertainty principle, actually. That's all about the paradox. And of course, we thought later on it was found that this is not completely true, because what in the quantum mechanics it was found that what Einstein EPR thought, EPR considered the local realism of consider quantum mechanics as local theory, but now we know that quantum mechanics is non-local and it can show this kind of prediction. So now, having said that, now okay, this is just about the EPR paradox. Now, if I want to show this EPR paradox in lab, or if I want to create a scenario like EPR paradox in lab, so what are the criterion, actually? What I have to satisfy, or what kind of measurement, or what kind of output I have to get to say that I am in an EPR paradox regime? For that, in late 80s, Red and Drummond, they proposed a criteria. They said that if, let's say, you have two distant particles and you are making measurement only on particle A, and then from that measurement, you are inferring the properties of other particle which may be far apart, actually. So in that case, what you do, you are making measurement on system A only. From that measurement, you are inferring what is the uncertainty in the measurement of other particles. For example, if you do the measurement on the position or measurement uncertainty, or inferred measurement uncertainty is this one, and then inferred uncertainty in momentum is this one. If you look at the inferred uncertainty product, or is also sometimes known as conditional uncertainty product, if it is coming less than h bar square by 4, then you say that you are satisfying the EPR argument. And then the experimental verification of this kind of scenario in the continuous variable, basically along the spirit of EPR, was demonstrated by Jeff Kimball and his group in 1992. And then in that experiment, they, instead of looking the position momentum, they look at the quadrature operator of the field actually. Now the coming to the actual realization. Actual realization means EPR paradox in its original form was demonstrated by Robert Boyd group in 2004, where he has shown the EPR paradox in its original form. Original form means in terms of the position and momentum variables. So what he did basically, or his group did basically, they looked at the photon pairs created by the BB by spontaneous parametric down conversion process. They looked, or they may map to the position correlation by using an imaging system to their detection plane. That's how they obtain the position correlation. Basically, they fix one detector and then scan the other detector and look at the correlation between the arrival of the photon over the position. And then the far field correlation, for the far field correlation, they developed a far field system, basically a Fourier lens, which basically Fourier transformed the BBO crystal to their detection plane, and they did the same measurement. And with that, they got the correlation, basically position correlation and momentum correlation like this. And from there, the uncertainty in position and uncertainty in momentum correlation, basically they are conditional or inferred uncertainty. And then their product, they have obtained like 0.01 h bar square, which is definitely less than h bar square by 4. So that's how they looked, or they demonstrated original EPR paradox in the lab experiment. So now, of course, having said that, this is, as I said, this is a fundamental experiment actually. Later on, people have used this kind of system for application purpose actually. So I would like to show just one example where people have shown this spatial quantum correlation for the application, for example, quantum imaging actually. So this is done in 2009 by an Italian group. So what they did, they basically, they have again spontaneous parametric down conversion, photon pairs created by spontaneous parametric down conversion, and they look, or they basically look at the far field. Basically, they use a Fourier lens, and they looked at they basically map these position correlation to momentum correlation on a CCD actually. So instead of just scanning other detector, they project whole beam on the EMCCD camera. And then what they said that, since there are position correlations, then the manifestation of position correlation could be if you look at the noise difference between or spatial noise, basically how the photons are arriving, the spatial at the different spatial regions. If you look at the spatial noise in these two beams, it can be cancelled because of these quantum correlations. So what exactly they did? They defined a parameter called noise ratio, basically, which measures the difference, variance of the difference noise actually. Since the two photons arriving here, their positions are correlated. So what they did, they look at they capture one image here, and they look at the difference of these two images, and there, whatever the common correlated noise, you can cancel it out. And they basically define this noise ratio, which is basically variance divided by mean. And you know that for the coherent state, it has to be 1, that is called short noise limit. But for the quantum states, like the states generated by the PDC process, they could get this noise ratio less than 1 actually. So that means they can get this advantage in the noise reduction, because classically, or with our all classical scheme, we can go up to short noise limit actually. But in this kind of scenario, they can get the noise ratio, or basically noise in your beam or your spatial profile less than that is allowed by the short noise limit. Moreover, this is just a demonstration, but very recently the same group have demonstrated that this kind of experiment, this kind of noise reduction can be implemented in kind of quantum noise in a quantum imaging scenario, where if you place one object in one path of your beam, and then you image that by using your imaging lens on an EMCCD camera actually. And then if you directly measure this, if you directly measure the or look at the image of the object, you get like the image like this actually. And on the other hand, if you do some kind of classical differential measurement, you do image like this. But at the same time, if you do imaging of this object by using the quantum correlated beam, then you can get really enhanced contrast or enhanced resolution in your image. So the central idea is, there is an image, but it has a lot of background noise actually. So that background noise is subtracted by using another reference beam, and then because since these are the quantum correlated beam, their noises are also correlated actually. So if you subtract out the correlated noise, then you can you can enhance the imaging scenario and enhance the resolution of your object that you want to image. That's how they have worked out it. So one thing I would like to tell you, that these initial experiments with the SPDC photon source, of course, they have provided a significant insight on spatial quantum correlation, and of course, they have demonstrated the quantum enhanced imaging and other sensing experiments also. But one of the main drawback in those experiments are they are really single photon regime actually. So you have to take thousands of images, hundreds of thousands of images to get this kind of pattern. So you have to acquire maybe millions of images to millions of shots in your CCD camera to have this one. So that is one of the limitations of those experiments. Now of course, a natural question is, can we have spatial quantum correlation with a large number of photons, or mainly macroscopic regime? Macroscopic regime, when I mean to say that where you can see really your beam is no longer a single photon regime, where you have to have a sophisticated single photon detectors actually. So to address this question is, yes, we can use bright twin beam light generated with the four-way mixing in hot atomic vapor to look at or to remove some of the main drawbacks of the SPDC photon pairs. So how this method works, I will tell you about that, and then remaining talk will be focused on some of our experiments or experimental research that has used the beams, bright twin beams generated with four-way mixing experiments. So what in this experiment we basically do, we interact a strong laser beam and a weak beam in an atomic medium. Basically, we take rubidium vapor, and then in that rubidium vapor, we just make some configuration that called double lambda configuration. Basically, what we do in this atomic system, we absorb 2 photons from our laser beam, and due to energy conservation, we emit 2 photons. And then in the presence of this input probe beam, this process we amplify. This process gets stimulated or amplified, and that in turn generates bright beams actually. That is the whole idea actually. Basically, you can do spontaneous four-way mixing also. To stimulate this process, we start with some input seed beam, and then stimulate the process, and at the end you can get bright twin beams actually. So with those bright twin beams, it has some significant advantages, as you can say that you can see that if instead of a single photon pairs, if I have a stream of photons or a bunch of photons coming together, then we can get statistically significant results in noise reduction in very small number of images. Moreover, the signal to noise ratio in quantum enhancing and quantum enhanced sensing and imaging scales at √n. So more the photons you have, better is your signal to noise ratio. That's how you can win by using the bright twin beams. And on the other hand, we are generating these bright twin photons with the atomic system actually. So that can have another added advantage, that if you want to in future, if somebody wants to work with, you want to store these kind of photons in the quantum memories which are based on the atomic system, then these photons can be compatible with the atomic based quantum memories actually. And this is like from practical perspectives, it has a lot of significance. And on the fundamental perspective also, it is like a significant, because thing is, most of the quantum optical experiments are done with a single photon regime. So how things are changing from moving to single photon regime to a bright regime, that is some interesting avenue that we are looking at. And then over the past few years, we have done a lot of study along these directions, starting from first experiment where we show that, of course, we can observe spatial quantum correlations with those beams. And with our very recent work, where we have used those beams something along the line of quantum cryptography actually, where you can encode information in those beams actually. That is now in Science Advances. So hopefully in a couple of weeks it will be out. So with that, I would like to now focus on how do we study spatial quantum correlation properties on our system. So as earlier I said, when we have spatial quantum correlation properties, we look at the position or momentum correlation. And moreover, if you look at the momentum correlation, they are directed, or they are basically governed by the phase matching condition actually. So here, opposite to spontaneous parametric down conversion, where one photon was converted into two, here two photons are converted into two actually. Sum of the momentum of two has to be sum of momentum of these two actually. And then with this typical phase matching condition is given like this, and it has a kind of sync profile actually. What does sync profile means? Sync profile means that if it is not even zero, still there is some efficiency, or there is still some efficiency of generation of photons actually. That means there is a tolerance, there is some tolerance on delta K actually. So that tolerance is interesting in our aspects, that if delta K was zero, if delta K was zero, then you are just getting point-to-point correlation. But since there is some tolerance on delta K, there can be some tolerance on delta K. That means the photons that you are creating with your nonlinear optical interaction, it will emit photon on a cone which has certain width actually. You can have photon which are correlated in this region actually, or there are multi-modes actually. It's not just a single spatial mode. You have multi-modes actually. And then in some of the earlier studies, people have shown that this kind of system supports images actually. They support the multimode. What I mean by multimode, that you can put some mask or some imaging, some mask, some pattern to one of your seeding beam, and then you can transfer that pattern here and here. You can basically generate your probe and conjugate, or your twin photons or twin beams with arbitrary spatial pattern actually, which is not present. Other regime where people work with the bright entangled photons or entangled beams is with using cavity actually. Cavity can also generate entangled photons in the bright regime, but in the cavity you can't have this kind of freedom actually. You will not have the multi-spatial mode actually. So for the quantum imaging kind of experiment, this provides an ideal avenue actually. So having said that, how in lab we have done the spatial quantum correlation of the bright beams. So for that, what we have done, so I will explore here. Now the experiments are similar to what the SPDC people have done. So this part is basically for the generation of bright beams, as I discussed actually. We interact a pump beam and input weak probe beam inside a atomic medium, and then generate probe and conjugate, which are bright beams actually. And then here in this particular experiment, we have looked at the far field correlations. That means we have used an imaging system. We have used a lens system that is kept in F to F configuration actually. And then we have recorded the images of our pump and our probe and conjugate, we call probe and conjugate this generated beams on a CCD camera actually. And of course, care has to be taken while acquiring images on a CCD camera. So for that, we have used we have pulsed our pump and probe beam, and then this is our pulse sequence actually. So we basically what we do, we created pulse of probe and conjugate beam, and we acquired these pulses on an EMCCD camera. And this EMCCD camera we use in a fast kinetic mode where 2 frames are acquired. 2 frames of, this is conjugate, this is probe. These beams are acquired in an interval of 2 frames are acquired in an interval of about 60 microseconds actually. Now, what we are interested, as I said, we are interested between the quantum correlation of the noise of this and noise of this. Okay, this is a beam. This is the image of the beam, but it has a bright DC background actually. What we did, we subtracted this DC background by doing the difference measurement. We subtracted the frame acquired in 2 consecutive images, and then we got we obtained the noise of basically intensity noise in this beam and intensity noise in this beam actually. And once we have obtained the intensity noise in this beam, then we can look at the noise reduction or quantum correlation or whatever things you are interested in. But one thing we have to note that since we are looking in a far field correlation, and then that due to phase matching condition, the correlated region probe of our twin photons, they lie in a diametrically opposite side actually. So to subtract it, so what we did, we rotate one of the image by 80 degrees. We subtract these 2 images. This is the probe noise. This is the noise, intensity noise in one of the beam. This is the intensity noise in the other beams. So we subtracted those to see that whether we have intensity noise reduction or not. So basically, when we subtracted it, then we got this kind of pattern, and ultimately we looked at this ratio, which is variance divided by mean. And as a result, we got some result like this. So this is for the typical laser beam actually, for which we are limited up to short noise actually. Our noise ratio has to be, it is 1 for the laser or for a coherent state. But for the state that we have worked with, we have reduced the noise beyond the short noise limit actually. So that's how we have obtained noise reduction in spatial domain, or we call that spatial squeeze. On the other hand, when we don't rotate, because thing is we are subtracting this with this one. So basically we are subtracting the correlated noise. Once we subtract the correlated noise, we get reduced noise. On the other hand, if we don't subtract the correlated noise, then we should get excess noise that we have verified. If we don't rotate one of the beam with respect to other, we can get excess noise actually. This is a sanity check. On the other hand, one important aspect here we have to look at it is, if we want to look at whether the correlation of this beam and this beam, it is a point to point or point to area. For that, we did some kind of cross correlation measurement. For that, what we did, we basically select one small region in one beam and scan that region with the other beam actually. We select one area and look at the cross correlation of this with other beam, and then scan over the whole beam actually. And then as a result, what we saw that for probe and conjugate or twin beams that we have generated, we got a typical scale of correlation. That typical scale of correlation we call as a coherence area actually. And then for our experiment, it came about 10 by 10 pixels. And on the other end, if you do the same experiment with the laser beam, there are no correlations. So you don't expect any correlation or any cross correlation results in the with the typical laser beam. So that's how we have looked at the spatial quantum correlation of properties of bright twin beams. Now, having studied those, now our next motivation was, okay, we can demonstrate this spatial quantum correlation. Then now the next thing is, can we create EPR paradox kind of scenario with our bright twin beams? Basically, can we violate this kind of relation? Actually, these are the conditional uncertainty product or inferred uncertainty product. Actually. And that in the next work we did that. Yes, indeed, these beams can create this kind of EPR kind of scenario. For that, the experimental scenario is same as what Robert Boyd done in earlier experiment with the SPDC. So we have to look at near field correlation. For that, we have to design an imaging system that images the birth zone of these beams, and then in the far field, for the momentum correlation, we have to look at the Fourier transform of their birth zone. So we recorded the image in the near field and far field, and we did the same analysis what we did in the spatial quantum noise reduction. As a result, here also in the near field also we could see the correlation, and far field we could also see the correlations. Basically, near field correlation will give me the information of the position correlation, basically delta square Rx, and on the other hand, far field correlation will give me the momentum correlation, or basically the width will give me uncertainty in the momentum distribution of photons actually. And then what we found, we calculated the uncertainty product, and ultimately we definitely got less than what is needed to violate the conditional uncertainty product. So thus we claim that we can show the EPR paradox in this kind of beam. Moreover, one interesting thing, as I was motivating you, that why we are looking at with the bright twin beams, even if there are the similar studies exist in the SPDC. So now my claim was, we can show this kind of statistically significant result just with a few number of images. So here we have looked at, looked at the uncertainty product for very less number of images ranging from 5 to 200. Even with the 5 images, we could see, or we could demonstrate the EPR paradox actually. So this is the limit. We are far away from the limit. That's how these kind of experiments will help you. Moreover, as another measure is, we have demonstrated the spatial entanglement in this kind of beams. Basically, spatial entanglement means position and momentum entanglement in those beams. For that, we have satisfied the DGCZ criteria. Basically, we looked at as I said, we look at the noise reduction, basically squeezing in the near field as well as far field. And then what we saw, according to Duan criteria, for the for satisfying the entanglement, your inseparability parameter has to be less than 2, and we got 0.67 or 0.63. That proves that indeed these beams can show EPR kind of paradox or spatial entanglement. So having verified these things, they are showing the EPR kind of paradox, and as well as they can show the spatial entanglement. So now the latter goal was, since we said that these beams can support a large number of spatial mode. So now our goal is, or what we wanted to look at, can we use this kind of beams for spatial information encoding actually? Can you encrypt some information in those beams? That question we try to address. So the setup is similar what we did in the earlier, but what we did, instead of just using a mirror there, we replaced mirror by an SLM, a spatial light modulator. And then what we did, now the goal is we want to encrypt some information. We want to encrypt some spatial information in those beams actually. So for that, the more elaborated figure is here. So we use an SLM in the POM beam actually. And then let's say we want to encode some spatial pattern actually. So then for that, we created a hologram for that. And that hologram, this is basically a phase hologram. And we imprinted that hologram on the SLM. And then we image this hologram. Basically, we image the pattern that is encoded to beam to the cell actually. And then finally we did the Fourier transform of this, or we looked at the things at the far field. At the far field, basically we should get the information of this object. So the whole idea is we wanted to encrypt this information in the twin beams actually. Okay, that was the whole idea actually. So for that, so what I would show that some of the results that we have achieved. So we use basically two spatial patterns, and these are the corresponding holograms. And then these are the one interesting thing is, if you look at, you encrypted some information in the pump, and you want to see that whether that encrypted information is shared between the twin beams that you have created actually. So indeed, if you look at their just DC profile, if you look at just their images, you don't see any pattern actually. But if you look at the cross correlation, if you do the cross correlation measurement between these twin beams, then what you see, you can see the encoded pattern. So these are the target pattern that we wanted to encrypt. These are the simulated results that we were expecting, and these are the experimental results. So you can see that we can clearly demonstrate, or we can clearly decrypt the information that we have encrypted in our system. So on the other hand, of course, this can have application in quantum cryptography and quantum communication actually. So now the natural question is, can anybody, so if thing is, I'm saying that to decrypt that information, you have to look at the cross correlation. Now the question is, if somebody has only this one or only this one, then if he or she can detect it or not actually. For that, we did the analysis, and indeed we found that the answer is not actually. So we cannot decrypt the information what was encrypted. So this was the autocorrelation of the probe conjugate, and this was the simulation. So this is not giving, or this is not revealing the information that we have encrypted actually. So that's how it can have application in secure quantum communication or secure quantum cryptography. So moreover, we did more control over that. Not only encryption, you can control over the pattern that you have created actually. For that, what we did, we did some some very smart things. So the four-way mixing process, as I said earlier, it involves two pump photons and two probe photons, two twin photons rather, probe and conjugate actually. And of course, they have to satisfy this kind of phase relations actually. And then what we did, by changing the relative phase between probe and conjugate photon, you can control the cross correlation pattern. Basically, you can, let's say you are getting if there is a zero phase between probe and conjugate, and if you change that phase to pi/2, you can get the negative of this. And by changing that phase between probe and conjugate, you can basically hide this even within the cross correlation, hide the encrypted information in the cross correlation measurement. Moreover, now one natural question will come. Of course, you did this cross correlation measurement, you encrypted information in both the beams. Of course, it is not available in the single beam, but how do you claim that it is quantum actually? So that is another question we have tried to address. For that, what we did some temporal measurement. Some temporal measurement means we did some squeezing measurement, basically intensity difference squeezing measurement with the different spatial pattern. So what I mean by saying that, so instead of EMCCD camera, we just replace, or you can use a flip mirror. You can use just a flip mirror and then detect these beams on a photo detector and look at the intensity difference squeezing. And then it turns out that these beams with having the spatial profile in their beam. So if you look at, this was our short noise limit. This red trace was the squeezing or our squeezing without any pattern actually. And then this green and blue traces were with two different patterns that you have used. So with those all patterns, the spatial squeezing or sorry, temporal squeezing or intensity difference squeezing was persistent actually. That means the quantum natures or is even persistent there actually. That's how we have verified that there is indeed quantum correlation present in those beams. So with this, I would like to conclude my talk. So what I discussed in last 45 minutes, so I talked about, spatial quantum correlation properties. How do we generate those, or how traditionally people have used the SPDC photon source to learn the spatial quantum correlations actually. Moreover, now, then I said, we work on the bright twin beams, and then of course we use four-way mixing in hot atomic media, hot atomic vapor to create these kind of beams, and then study this spatial quantum correlation or the EPR paradox kind of situation with the original position and momentum degrees of freedom in the bright regime. Moreover, the last but not least, what we have shown that these spatial quantum correlations can indeed be useful for quantum cryptography and quantum communication. And then, of course, it just opens a path toward secure high capacity information encoding and information processing. So with this, I would like to acknowledge the people with whom I have collaborated, who have contributed. So Alberto Marino, who was in University of Oklahoma, now moved to Oak Ridge National Lab, and the collaborator with whom I have worked, and then my PhD students at IIST. And with this, I would like to thank you. And if you have any questions, I would be happy to take it. Thank you.
Hello, the floor is open for questions now.
Yeah, there is a question I see in chat box that says that I don't understand a thing. Measuring at one region, I can infer the measurement result at the other position. This is in fact true in classical Newtonian case. What the paradox then? For example, if a bomb explodes and two of its fragment can go different ways, then by measuring the momentum, one can infer the measurement of the other. Okay, so I understand that what you are saying, what we are talking about, that if we are talking about the state of a system, actually we are talking about the quantum particle or quantum system. So if you can't talk, when you talk about the microscopic particle, you can't relate with the classical Newtonian mechanics actually, where the Heisenberg uncertainty is almost negligible actually. Uncertainty product is negligible. Here, what I was telling you, when you talk about the EPR paradox, so what I think you need to look at EPR paradox, what it says actually. So I have a pair of particles which are perfectly correlated in their position and momentum, and then if I make them space-like separated, and then if I do the measurement on the particle which is in my lab and other particle which is space-like separated actually. If I make a measurement on a position of particle, I could infer the position of the other particle. And then on the other hand, if I do the measurement on the particle, I could infer the position of momentum of the other particle, which is far apart from me actually. So what it appears, or what their logic was, since they are space-like separated, there is no instantaneous communication happening. So since sitting in my lab, I can infer the position and momentum of other particle which is infinitely distance away from me. That means it appeared that the other particle which is infinite distance away from me is carrying definite position and momentum actually. That's how the whole paradox is. That's how this paradox is all about actually. It has definite position. It appears that it is carrying definite position and momentum actually. So or the uncertainty product is kind of zero actually. That it appeared to be by applying the local theory. So yes, I hope that answers the question.
Any other question?
Yeah, I have two questions. Can I ask?
Please,
Yeah.
please go ahead.
Yeah. Thank you for your presentation. So my first question is to initiate, for example, in QIQT3 SPDC, one needs intense or strong laser intensity as compared to QIQT2.
Yeah.
Moreover, you will have self-phase modulation effect apart from cross-phase modulation. So question is, any reasons why you have selected QI3 as compared to QI2 for SPDC?
Yes, yes. So one, as I have told, of course, if you look at the very first experiment that Slusser done in 1985, he used the QI3 medium in the atoms to generate the squeeze light. Okay, so but in late 90s, it was discovered by Scully and others that the configuration in the first configuration that Slusser used, it was a cascaded configuration. But the other configuration that we have used is a double lambda configuration. In that double lambda configuration, it was found, or it was predicted in late 90s, that it has enhanced Kerr nonlinearity actually. So that QI3 is enhanced in that kind of process, or that kind of configuration actually. That's why we used actually. On the other hand, whatever the available QI2 we have, we can't generate this kind of bright beams without using cavity actually. So the thing is, the configuration is what is giving us the enhanced QI3 nonlinearities. And if you compare with the power, of course, power is more actually. Power we are using 500. About 500 milliwatt, and on the other hand, SPDC people, they may use less than 100 milliwatt, but that is reasonable. That is not very, very critical, I would say, because what I want to have more power in my my twin photons, or the photons that twin beams that I want to create actually. So the answer to answer your question in one sentence is, this double lambda configuration gives us enhanced QI3 nonlinearities that allows us to generate the bright entangled beams with optimum lab conditions.
The second question, do you have any plans to use polarization degree of freedom of light in your experiments?
Yeah, not immediately, but recently, one leading group in China actually, they are very ahead of things actually. They mainly in quantum actually. They are one thing actually, the group has shown that, of course, the same system actually, if you dilute your pump a lot and then you can generate, or you can mimic the similar kind of experiment what people do in the SPDC setup actually, where you create a pair of photon, or you look at the polarization, correlation and all. Indeed, it is possible. I also plan to switch between discrete and continuous variable. I may do that in near future actually. Just with the same setup, looking at discrete and continuous variable quantum information.
Thank you.
Yeah, sure.
Okay, so I think we are running little out of time, and it's time for the next talk. That was a really interesting talk, Dr. Ashok. Thanks for the same, and we'll move forward. Okay, kindly unshare theoretical physics at the University of Vienna for research on quantum reference frames, entanglement in quantum field theory and quantum causal structures, working under the supervision of Professor Bruckner, after which he moved to the University of Queensland as a postdoc researcher, where he worked on methods for discovery and control of causal structures in quantum systems, with applications to quantum technology and to the joint foundations of quantum theory and gravity. So welcome, Professor Costa. And the title of his talk today is Costa, And the title of his talk today is Quantum Causal Structures. Professor Costa?
Hello?
Hello, yeah. Welcome, Professor Costa.
Yeah, so if I can share the screen, how do I share the screen?
Yeah.
I think I need
so there's a button. Yes, you see a green button which says on the top, share content. There's a green tab on the top panel, share content. It says share content with an arrow, upper arrow.
Upper arrow, sorry, I am on Zoom.
Do you see the top panel? So there's there's the audio, then there's a video, then there is a share content. So there's a box with an arrow.
So I have a share screen, but it says host disabled participant share screen sharing. So I think I need some host permission. Yeah,
sorry,
can you change the, yeah,
sorry.
good.
I think you can do
Can you try it again?
Yeah, yeah. Okay, can you see the screen?
Not yet. Yes, now. Yes, we can see it. Huh? Dr. Costa? Yes, yeah. Please make it full screen.
Yep.
Yeah, thank you. Start.
Okay, so can I start? Yep.
Yes, please start. Yes.
Okay, yeah, thank you everybody for being here, and thank you for inviting me to this online session, Kolkata and the world. So please, if you can send me some notification. So I have 45 minutes, right? Maybe I'll. Okay. Try to stick to that.
Around 45 minutes and then 15 minutes of questions.
Yeah.
Yeah.
Okay, so I thought to start by saying a couple of words about me, but I've been given a very nice introduction, so I will not have to say much. Maybe since we are meeting remotely, I will just share a picture so I can see a bit bigger picture of myself. I'd like to say I'm the one in the middle, but unfortunately I'm not. I'm the one with the beard. So that's me, my son, and my partner. And so I will go very briefly because this was already mentioned. My life history has taken me around a few places. I was born in Milan, in Italy, in the last century, where I did my undergraduate studies. I lived for a while in Vienna when I got my PhD. And then I was for quite a few years in Brisbane, in Australia. And very recently, I moved to Stockholm. I'm currently not in Stockholm. I'm back in Brisbane for some travel accidents. No, not accident, but for current traveling. So what do I want to talk about today? Quantum causal structures. I want to give a bit of an overview about the field I've been working on for the last several years. And this is a field that in fact arrives is the combination of many different motivations. So I will give you just my perspective, how I got interested in this. And that is, one can think very generally, how do we describe things in physics? And you can get a sort of very common picture. For example, if you're talking about quantum physics, you may want to say, what are events? Events are some observable things that we can see. We can think of events happening in space-time. And how we describe these events, typically what we need to do is to assign some quantum state in the past of all the events we want to describe, and then we evolve the state, and then we make measurements, and then we evolve the measurements. And then if we have some light construction, there could be some causal influence. For example, event A here can influence event C and not event B. And you can start to abstract this type of reasoning, and you can very easily see that you can abstract everything into some kind of circuit model where you have some initial state and a set of quantum systems that evolve, and you can describe your events through, for example, measurements and the evolution through some gate. So the common thing in all this way of thinking is that all the events have a definite causal order. So you can always say, and a definite causal structure. You can always definitely say A cannot influence B and A can influence C. And if A can influence C, then C can definitely not influence A. So this is a very standard and basic way of which we do, I will say, almost all of physics. But there are a few reasons why one might think this is not the full picture. One of these reasons come from combining quantum theory and gravity. And so you will know that in general relativity, the presence of matter, of mass, distorts space-time, not only space, but really space-time, which means that in principle, if you have matter that is in superposition, this can create a quantum space-time. And if you start to try to put events on this quantum space-time, you so realize that you might end up in situations where you cannot really say if an event is before another or after another, because the light construction might be in a quantum superposition. So this is one of the motivations. And we have an article that characterizes a bit more in detail this scenario. Another motivation is that, in fact, if you start to think about these quantum causal structures, you soon realize that these can potentially work as quantum resources. And one can think, well, okay, it's maybe a very unfeasible type of resource, but then it turns out you can perform experiments that very closely simulate or reproduce those indefinite causal relations without any need of quantum gravity. And I will, if I have time, I will briefly explain at least one setup where you can perform this type of experiments. There are other situations where one may want to consider events without a fixed causal order, even in classical distributed computations. So for example, if you think about the internet or about any situation where you have a computation that happens at different nodes, and these nodes send the signals to each other, then it's actually a very well-known and very pressing problem to determine or understand the causal relation of events. Because if you start to have delays or some uncertainty in the way the signals are transmitted, you might not know a priori which events are earlier and which are later. So this is an independent motivation for thinking of scenarios without a causal order pre-assigned in advance. So these are all motivations, but how do we even start to do physics without having a background causal structure? Since this is the way we usually think about physics, we formulate most of our theories. And so what we have to try to think is that we want to describe these events in some space-time, but without really space-time. So we want to have a description that starts with these events without having a reference to background space-time. And so instead of a quantum circuit that connects these events, we need some more general type of object that connects these events. Now, one thing that one way one might get stuck in trying to understand this type of scenarios is what I will call the evolving state fallacy, which is something that, in fact, I will briefly discuss. That is also a problem in the characterization of more concrete things like non-Markovian open systems. So what is evolving states fallacy? That's the attempt to describe everything in terms of an evolving state. So, and that again, is something very common. You think that you have a system that you describe and it's evolving in time. And then the way you should describe it, this system, is by assigning a state at each time. So if you have a quantum system, that will be a density operator. And so you say there should be a density operator at time 1, time 2, time n, and then maybe you try to find some evolution equation. Now, to give some sense of why this is not a good idea, try to understand, to think about this scenario. So this is the weather prediction for tomorrow in Kolkata. I didn't take the prediction for today because it was 100% rain at some point. So I tried to find something a bit more interesting. Now, you see that here they give you a percentage of chance of rain at each hour or at each interval of time. So this is, if you think of this as an evolution of some state, the state here is something like the probability to get rain. And now I can ask you, what is the total probability to get any rain in Wednesday? Can you deduce it from this time evolving probability? And well, if we were in person, maybe I will try to get a raise of hands. Maybe you can think for a second how we will try to compute these probabilities, but maybe I will just give you the answer. The problem is you can't. So the reason is that what you're given here is a sequence of marginal probabilities. So you're given the probability for rain at time 1, time 2, time 3. But what you need is the union of the probabilities at all these events at time 1, time 2, time 3. So the object that you should be considered is not this sequence of probability distribution, but a joint probability distribution across times. And the problem is, you know, there is a 39 probability that it trains between 2 and 3 p.m., but you don't know if this is independent of the previous times or the later times. You don't know if suddenly there can be rain and it's independent of the weather before or after, or maybe there is a big cloud and it's almost certain will come over, but you don't know at what time it's coming. So the crucial thing is if you have this time evolving picture, you will be missing some correlations across different times. So what you should really think about is that each event is some independent variable or some independent source of some independent random variable, and you should consider joint distributions even if they're distributed in time. So this leads us to try to formulate all advanced quantum theory. So instead of trying to think of a time evolving state, which will have as a classical limit this marginal probability distribution, we need something that is the quantum version of what we call a classical stochastic process, which is a joint probability distribution across all times. And so that's what I will try to present, what I will present today. How do we construct such a framework? And so the starting point is to understand how do we describe events. So we say that we have to focus on the description, to start from a description of events without a background causal structure. And here we should clarify that when we talk about events, there are different ways one can understand or define or think of events. And in physics, we mostly have two meanings of this word. One meaning is that is often employed in general relativity, or at least in some formulations, is that an event is a location in space-time. So, for example, a set of coordinates, so some geometric location. A different point of view is that an event is something that happens. So, for example, a measurement outcome. You perform a measurement on a system, this gives you an outcome, and that's your event. And this second way is the one that we can use as a starting point of our general construction, because if we can start from the quantum description of events, and to do that, we don't need a reference to our background of space-time. So when we talk about an event, it's not a location in space-time, but it's something that happens like a measurement outcome of a measurement. Okay, so this is our task. We need to characterize what are quantum events. And so when you go to kindergarten, you might be told that so a quantum event is something that something observable. For example, a particle has a certain position or things of this type. So the result of an observation. Many introduction one is told that observables are described by self-adjoint operators in quantum mechanics. That's not a very modern or very general view. The kind of elementary school version of quantum measurements is POVM measurements, positive operator value measures that I assume most of you will be familiar with. So this is a set of operators, E with the subscript A, and A is your measurement outcome. So it's telling you that for what are the possible outcomes of your measurement. So you have a quantum system coming in, you perform some measurement, and then you have a possible outcome. Now, this description is actually not sufficient for what we need to do, because this only describes the probabilities to get some outcome when you perform a measurement, but doesn't describe how your system is transformed. But now we want to describe events that potentially are time-like separated and can influence each other. So we need a description of event that also takes into account how the system is transformed upon measurement. So here comes our high school version of definition of a quantum event, which is quantum operation. So that's the most general way quantum mechanics describes an event. And in a bit abstract terms, this means that you have to consider an operation that maps some input space to an output space. So these spaces are spaces of density operators. So these are quantum operation is something that should map a state into a state, any state to any state, and these are known as completely positive maps. This is the bit more formal definitions, but if you're not too familiar, just think that this is the most general transformation that you can associate with any operation or any transformation of a state. As a concrete example, you can think of a projective measurement. So if you perform a measurement that tells you, I found my state, my system in the state psi, then the operation corresponds to projecting your initial state to the state psi. And so in general, these operations include non-deterministic operations with a possible measurement outcome. As a particular case of operation that is useful to construct the theory is deterministic operations. So you can think of these as scenarios where you make a measurement, but you forget about the outcome, or you don't consider, you discard the outcome, or even just transformation, deterministic transformation on the system that you may want to describe. And so these are, as before, completely positive map, but with additional condition that they're trace preserving. And the reason is that states have to be normalized with trace equal 1. That is what telling you that probabilities are normalized. And so a deterministic operation is one that preserves the trace of the state. As a particular example is, for example, a unitary transformation. Your state comes in and then you rotate it according to some unitary operation. In this case, there is no measurement procedure associated, but it's still one example of a quantum operation. And more generally, if you put everything together, you get what is called an instrument. An instrument formally is a set of CP maps, so a set of non-deterministic transformation that sums up to a deterministic transformation. So this label A represents the measurement outcome, and the fact that all the maps sum to a deterministic one is simply representing the fact that you are considering all possible outcomes of your measurement. Okay, so this is our description of events in textbook quantum mechanics, and this is our starting point for our construction of quantum mechanics without a background causal structure. So what do we need to do? Is what should we try to get in our construction? We should try to get, as we were saying, the joint probabilities for events. And the point is that these joint probabilities, we want to get them through a formula that doesn't care what is the doesn't care about the causal relation. So something that in pictorially represents this blob around these boxes without telling what is the order or the connection between these boxes in advance. Now, a couple of technical slides here. If you make some assumption, which can be summarized in assuming that locally you cannot distinguish your model from quantum theory, so all your operations are consistent with getting a quantum system in, measuring and sending it out, then you find that this probability can be written as multilinear functions of your CP maps. So each event at each location, which we can imagine as a local laboratory, will be associated with some CP map, and the joint probability will be given by a multilinear function. And you can derive this axiomatically from some requirements that represent local quantum theory. And this function is something we call the process, and is in a way a generalization of what we call a state, because it's what gives you the probability for a set of events. Now, this is a little bit abstract, but it becomes a bit easier when we introduce something called the isomorphism. So this is something that maps, that connects maps to states. So if you have a map that goes from, that is defined as a function from an input to an output state, space, this can be represented equivalently as a state that lives in the tensor product of input and output. So you can think of, instead of describing a transformation from input to output, you are describing something like a 2-time state that is defined across the tensor product of input and output. And here is the technical definition. Again, I will not enter too much in details. But so this is just to say that this is defined as a joint operator as if it was a density matrix with subsystem input and a subsystem corresponding to the output. And if you describe maps in this way, then you get a very familiar look of this general probability rule, which is simply a trace rule formula. Different sources define it with different notation, conventions, transposition. But the main thing is that you have your joint probability will be given by the trace of the tensor product of all your CP maps. times an object, a matrix that we call the process matrix, which is defined in the tensor product of all input and output spaces. Just to mention that formulas of this type have been derived over the year over and over. So it's a very powerful tool that people have discovered in many different contexts. Now, this is very similar to, now the question is, what is this process matrix W? So this is now the central object of our study, that what characterizes quantum causal structures. A way to link to what we know, the formalism we know about from quantum theory, is that now these measurement operators MA and B represent what in the usual formalism are observables, with the only difference that now these describe can also describe transformation. But formally, they just work like observables. And this process matrix formally just looks like a state. In the sense that if you have an observable and a state, your probability rule has exactly the same form. The new thing is that now, even if we think of it as a state, this is a state that does not, that it can allow arbitrary causal relations between these events. So in the usual formula, you will have instead of W, you will have a state, and instead of A and B, you will have say P of M elements. And then in that case, there cannot be any signaling between these different events. So if you discard the outcome of, say, measurement A, then there is no change in the probability distribution for B. But now in this case, there can be causal influence. So W can encode, because it can encode arbitrary correlations between these measurement outcomes, it can also encode the signaling correlation. So it can also encode the causal relations. And all the causal relations are somehow incorporated into this process matrix. Which is, it works like a state, but with some constraint that ensure normalization of probabilities. So to get a little hang of it, we can go through a couple of examples. So we focus on bipartite processes. So we have an event A and event B. And now we can think of what are all the general causally ordered scenarios, so the usual known ones. How does this process look for known scenarios? So the simplest scenario is where A and B are two measurements on a bipartite state. And in this case, the process looks like a joint state across the two input spaces and identity over the output spaces. So if you plug this W into this formula, then you will get probabilities that are exactly the same as the usual Born rule given a state rho. Different scenarios where A is before B, so there is signaling from A to B, but not from B to A. In this case, the process matrix is a tensor product of a state that goes into Alice lab, into the lab A. And then you have an operator T that is the Choi representation of the channel from A to B. And so you start to see here some structure that you have encoded in the process are all the correlations. So the channel T that goes from AO to BI, it's what correlates, for example, a state preparation that Alice can do and the measurement that Bob can do. And Alice's measurements will detect the initial state rho. So that's a second known case. That's how a channel from A to B looks like in this formalism. A bit more generally, we can have channels with memory, which is the situation where the system that goes into Alice's lab is correlated with an external environment that does not go into the lab, but that can interact with the output prepared by Alice. And after this interaction, it goes into Bob. So this is what is called a channel with memory. And again, if you plug this W into the general rule, you will exactly get the probabilities from causally ordered scenarios. So this is actually some interesting general case, this channel with memory, that is worth thinking about, because already in this case, even if the events are causally ordered, this is already one of those scenarios where this time evolving state picture doesn't really work. So already in this case, we can see that the quantum version of what of this classical stochastic process is this process matrix. And it's easy to see that if you just try to build the state, say that here you try to build the state that goes into Alice's lab, and then you try to build a state that goes into Bob's lab, and you only give this information, this will not be sufficient to recover all the correlations between Alice and Bob. So this gives the answer that is useful for the study of non-Markovian systems, and gives you the quantum version, the quantum analog of a classical stochastic process defined as a joint distribution of variables across time. And this is something called, can be called a quantum combo. It has different names. We call it a causally ordered process. Yeah, and as you said, it can involve an arbitrary interaction between a system and environment. Something to note here in this description, again, I want to stress that this W can be considered as a state over time, which is something that you don't do usually in quantum theory, emphasizing this concept that if you typically, when you consider time evolving systems, you give a state at different times, but you don't give a joint state across times. You can give a joint state across different systems that can be separated in space, but if you have events separated in time, usually you don't give a joint state. But here, when you have this process matrix, it can be seen as a state over time. So these input and output spaces can be seen as a temporal subsystem. So a subsystem at time A, and a subsystem at time B. Formally, these are represented exactly like subsystems in quantum theory, in the sense that you build a joint space using the tensor product. Now, this is everything about causally ordered processes. But now we want to know, okay, is this the most general thing we can think of? And some generalization that becomes quite natural in this formalism is a situation where the causal order is not known. So concretely, you can think of a scenario where you toss a coin, and with some probability you put event A before B, or with some other probability, you put event B before A. So this is a scenario that doesn't have a natural description in quantum theory, because in a usual formulation, you need to set the causal order of events in advance. However, in this formalism, it has a very simple formulation, because you simply take the convex mixture of a process that has A before B and another process B before A. And these are processes that we call causally separable. So this is similar to the notion of separability as opposed to entanglement. So something that where I can imagine that there is an underlying causal order, but you just don't know which one it is. And of course, one of the questions of interest is this the most general scenario? And it turns out it's not the most general scenario. There are things that are called indefinite causal order. So something like a situation where I cannot even imagine a classical hidden variable that determines the order. Now, there is a mathematical example that can be written in this way. These are Pauli matrices. Alice and Bob are both getting a qubit. So it can be formally proven that it's not separable, but this is not very enlightening, because it's not very clear how it relates to any. So this is just a mathematical expression, and there is no clear implementation or a realization as a physical process. However, there are, so this was the first one that we found in one of our first papers. However, there are some other scenarios that are a bit more intuitive. And to understand one such scenario in connection with the original motivation, which is causal relations in general relativity, you can think of a scenario where you have events that are defined by the ticking of a clock. So you define, you have two quantum systems, and you define event A as an operation that is performed, say, at the second tick of clock A, and event B is defined as the second tick of clock B. And you set up your situation such that if nothing else is around, these two are at the same time, so they're space-like separated. So there is no causal influence between them. But now, if you start to bring some massive system nearby, then you have that gravity induces time dilation. So now the second tick of event B ends up being in the future of event A. So crucially, from the point of view of B, his event is exactly at the same time, regardless where is the mass. It's just that the relative order with the event of A now changed. But of course, if you now bring the mass closer to A, then it's event A will be in the future of event B. So the causal relation depends on the position of the mass, and now we can think of making the mass quantum. So it can be in two quantum states, state right or state left. And then I will not go through all the details here, but just to say, if you prepare the mass in superposition, then you end up with something like a causal superposition of orders A and B. To be more precise, this is not really a superposition, but it's more entanglement between the position of the mass and the causal relation between the event. In the sense, and you can't really define this superposition without having this extra control system. But maybe a better way to think of it, this is quantum control of causal order depending on a control system. Here maybe I will go a little quickly through these details because it's perhaps a bit more formal, but just to say that this scenario has a relatively simple representation in terms of process matrices. You can actually, in this case, you can write your process matrix as a rank 1 projector. So you can interpret the state as a pure state. And the pure state is an equal superposition of two vectors that correspond to the two different scenarios. So the first is the scenario with the mass on the right. So the ket R represents the mass being on the right. And then you have a vector that represents the process AP4B. And then you have the other element represent the other branch of the superposition. And so here again, you can see clearly that this is something that represents entanglement between a control system, which is the mass, and a vector that represents the causal relation between A and B. Okay, so people call this superposition of causal order, but I'm actually not very fond of this term because it's not a pure superposition. You need this control. And now to briefly mention, so this was in this gravitational scenario, which is if you start to put together the numbers, what type of masses will you need? You will need really big masses and to keep them in superposition for a very long time. So nothing that is even remotely feasible with modern technology. But it turns out that you don't need giant masses to create indefinite causal order. And so here is another scenario that is a bit more concrete. So here you have a picture of a scheme of an interferometer. So imagine that from the left, you have a photon arriving, and then these PBS are polarizing the splitter. What they do is that if the photon is horizontally polarized, each PBS will let the photon through. If the photon is vertically polarized, then each PBS will act as a mirror and the photon will bounce. In the middle, these U0 and U1, these are unitary operations that are performed on some other degree of freedom, other internal degree of freedom of the photon. So not polarization, but it can be frequency, for example, or it can be spatial mode, so the shape of the beam, or anything like that. So we can see what happens if we start to prepare a photon in the horizontal polarization. So we have the control system can be in two states, 0, 1, which is, for example, vertical, horizontal, and the target is any finite dimensional system that is prepared in some pure state psi. So we start with the photon vertically polarized and see how it goes through. So it goes through, goes to U0, then goes through again, goes to U1 and goes out. So the final state in this case is applying first U0 and then U1 on the target system. And then you can see if you prepare the other states from the control. So now the photon will have to reflect each time it meets a PBS. And then we see reflects U1, goes around, reflects U0 and goes around. And so the final state you get in this case is first apply U1 and then U0. And then what we want to do, of course, is to start our system in a superposition of the two control states. And so what happens is that the state will just go through in a superposition of the two orders. And because quantum mechanics is linear, the final state will be simply a superposition of the two states I've shown before. And so this is exactly the same final state as we had when we consider the gravitational scenarios. And this is a process that is known as the quantum switch. So that's again the quantum control of the causal order between between U0 and U1. So this is yeah, as I mentioned, this is something that can be performed in the lab. There have been quite a lot of experiments. Of course, it's not a full simulation of quantum gravity because of the gravitational scenario, because here the time order is not given by a fundamental delay of the time, but is given by routing the system in the correct way. But still, if you look at what the process is doing in an information theoretic perspective, is doing exactly what it was doing in the gravitational scenario. So from the point of view of information processing, you have all your capabilities. And so as we mentioned, for example, you can get some computational advantage if you have this resource that cannot be represented as a quantum circuit. You can have an advantage in doing certain quantum computation, and there has been a lot of interest in recent years to try to explore more and more protocols where you can have an advantage. So I will very briefly mention other things you can do with the process matrices. So this was a quite broad overview talk. I didn't really touch on any recent result, but things that you can start to study is, for example, how can you communicate in the presence of indefinite causal order? So these can be a little puzzling at the beginning, because in a typical communication scenario, you have a sender and a receiver, and then you have to think of many repetition of a protocol where you have a sender and a receiver whose causal relation is always fixed. You always have first A, and then A prepares the message and B receives the message, and so B has to be always after. And so it can be a little bit confusing to think of this, but if you have this formalism, then it becomes quite natural. And you can calculate things like channel capacity and give bounds on quantum and classical communication capacity. Another thing that is maybe a bit more exotic, you can start to explore closed time-like curves. So these are models for time travel. The standard approaches to closed time-like curves have quite a lot of problems. But one can consider a model based on these process matrices that, in fact, doesn't have all the problematic aspects of other models. Another thing that one can do is that is, if you want to think in terms of these quantum gravity applications, to have some reference frame independence. And what I mean is that in the way I formulated the scenario so far, you still need some reference frame to define your events. So for example, in the gravitational scenario, this was the local clocks. And so these were assumed to be some background classical clocks that you can always tell when is, say, the 2 o'clock for the local background clocks. So that's what allows you to label the events as A, B, and C, and so on. But in general relativity, usually one wants to give a reference frame independent picture when you don't fix any background system. And so that's something that is, again, can be a little unclear how to do at the beginning, but in fact, it turns out you can give a version of this formalism that doesn't need this labeling. So these are just a few examples of some relatively recent works on this formalism. So, okay, so this is time to wrap up. So the main message is that it is possible to formulate quantum theory without having a global causal structure in the background. So you don't need to have in the background something like a state that evolves in time, or you don't even have to know in advance what is the order between the events that you want to consider. You can recover all the known quantum theory and even more general scenarios without assuming global causal structure. And indeed, there are situations that are compatible with the local description of quantum theory, and yet cannot be described in terms of any background classical variables that defines their causal order. So that's what we call indefinite causal order. And I have shown with a couple of examples that this is not just an abstract mathematical construct, but it is physically meaningful. And I have presented two physical scenarios. One is when you combine quantum and gravity, and the other is a scenario that you can realize in the laboratory. And importantly, this is a new quantum resource, so it's still under investigation. I will say how much one can really do with this type of resource that you cannot do with, say, ordinary quantum computers. But this is definitely something interesting because it's a new type of resource which can be accessed with the present-day technology. And finally, this is what I mentioned a little more tangentially, but this has a very important application to even to the study of causally ordered scenarios. and that is for non-Markovian open quantum systems. So as I mentioned a few times, if you try to consider general non-Markovian processes, so these are processes where your system interacts with the environment and the environment retains a memory of interaction of the system, then you cannot really describe those processes using time evolution. So also in those cases, you really need to use this description in terms of a quantum causal structure. So in this case, it's causally ordered causal structure, but you still need this type of formalism where you take an all at once description and your state over time, your process over time is described by a causally ordered process. And so this is a quite important application, and there are now it's something that is becoming increasingly popular, and it's a very rapidly evolving field study of open systems, of causally ordered processes. And so with this, I would like to thank you, and I can take any question from the audience.
Okay, questions, please. The floor is open for questions. Thanks for completing in time. Questions?
Yeah, may I ask something?
Yeah, sure, please.
Yeah, so the general form of a process matrix, does it always considers Hilbert spaces of states and channels, or can it consider something more? Like,
In the sense beyond quantum theory, or
yeah, so like for example, you showed that you showed one example where the process matrix was composed of the state tensor product with channels, and that can be like separable or in an entangled type of states. But in general, can the terms be something other than states and channels?
yes. So okay, already. So state and channel, I think you refer to this form, where you have an initial state and then a channel that connects the first to the second. Yes, already when you have a non-Markovian process, this is not just a product of a state. And this is because the environment creates correlations between operation at time 1 and operation at time 2 beyond the one given by the channel. So the way you can think of it is that a Markovian process is analog to a product state. So you have a product of initial state and then a channel from A to B. And then the non-Markovian channel is a correlated state, which can also be entangled. So for example, one of the insights here is that you can distinguish between an environment that carries only classical memory to an environment that carries a generally quantum memory. And this is exactly the same distinction, or very close to the distinction between a separable state and an entangled state. So if this process is formally analog to an entangled state, then this is the scenario that needs a quantum description of the environment. So you already for these causally ordered scenarios, you have a situation that is not just state and channel. But then if you go beyond causally ordered scenario, indefinite causal order, then you have processes where you cannot really tell what is a state, what is the channel, and yeah, there are different levels of generality, and at some level we don't even have a physical interpretation, and so you cannot really pull apart what you define as a state and which part you interpret as a state and which part you interpret as a channel.
Okay, so you cannot decompose it further.
Yeah, so already in this case, you already cannot decompose it further in the sense, if you have an entanglement, that the scenario where you cannot put it as a product of initial and final state, and then you have other scenarios where there is no even decomposition using an external environment. There is no interpretation in terms of states and channels.
Yeah, but you can still say that it lives on the space of A input, A output, and B input.
Yes,
but...
so the state space is always the same. So the state space is always the tensor product space of Alice space and Bob space. But you can have the general processes which, let's see if we have, already here, for example, you see that you will not have a simple situation where one of the two outputs is identity. And so the most general process is something that lives, has non-trivial terms in each input and output space.
Okay.
Yes. This is an example, for example, this is an example where you really cannot say what is the state. So you can, for example, take some partial trace and then define the state for Alice and the state for Bob, but these are really marginals. You cannot build the whole process by putting together those marginals.
Yeah, and will they be positive, the marginals? I mean, do they retain the property of states? Or
yes. So, for example, for this, and this is a completely general property. If you so one has to be a bit careful how to define reduced states, but if you do the partial trace on Bob's side, or more generally, if you plug in a deterministic operation for Bob, then you will have that the reduced process will be a state for Alice and on Alice input and identity on Alice output. And this is a completely general situation. If you have a multi-party scenario and you start to fix deterministic operation in a set of parties, then the reduced process will be a valid process. And if you fix everything except one, then the reduced process will be just a state.
okay. Also, one thing. So you mentioned that is this process matrix a resource that you mentioned at the end? Or
yeah,
you
so the process matrix itself is a mathematical construction, I will say, but there are physical situations that can be interpreted as it can be interpreted as resources. Yes.
Okay, like indefinite causal order, you can say it's a resource.
Yes. Yeah, we can say that. I mean, one has to be a little careful what exactly it means resource, but technically you can say that accessing if you have some information process that goes through some indefinite causal order, you can do some things better, or that or more things than you could do using, say, a quantum circuit.
So do they show advantage only in communication, or they can show advantage in other tasks as well?
Okay, yes. So there have been a lot of works showing advantages or claiming advantages on all kinds of things, from computation to communication to thermodynamics to all sorts of things. Now, to be fair, one has to be a little careful, because when you talk about advantage, you have to be sure you are comparing things in a sort of fair way. So when you talk about computation, for example, the type of advantage, there is one query complexity. So it means you're trying to perform some computation, and then you're asking how many accesses to some black box operation do I need to perform my computation. So in that case, you can make a quantitative comparison between putting your black boxes in a circuit or using them in an indefinite causal order. When you have things like thermodynamics, you can also define, try to define this fairly, but I will say it's a little less developed. So there are some claims that you can have advantages in many situations, but the comparison is not always made very, very rigorously, I will say.
Okay, thank you.
So, any more questions?
Can you hear me? Hello?
Hello?
Yep.
Okay.
Hello, yeah.
Yeah. So I'm not sure if this is a dumb question, but can we think of these matrices as like some kind of an entanglement across time, like?
Yes, in some case. So there are different ways to think about entanglement across time. Thinking about entanglement across time was one of the motivations to start this type of process. So I would say there are two main ways you can think about the entanglement across time. One way is if you just have an ordinary channel. So this is the sort of the simplest situation where you have a system, an operation at time A, and then another operation at time B later, and think that you have something like a unitary operation. Then formally the unitary channel from A to B formally looks like an entangled state between the output of A and the input of B. So this is something that has been noticed already in many different forms. One way you can think of it is that if you make some state preparation at A, or if you make some measurement at A and some measurement at B, you can get a perfect correlation. It can violate things like Bell inequalities. So people consider things like Bell inequalities over time. They're closely related to things called the Leggett-Clark inequalities. And so there is a formal way in thinking. So you can define just the ordinary evolution as an entanglement between an output space and an input space. And then another way is to think. So in the sense, entanglement is defined based on a subsystem division. So there are different ways you can decompose a process into subsystem. Another way to decompose is to think of a whole subsystem that defines event A and the whole subsystem that defines event B. Yeah, so you can also think about these non-Markovian scenarios where you have a quantum memory as defining entanglement across times, but in a different division of subsystem. So in this case, the entanglement will be between system AI and system AOBI. So you make a tensor product in a different way. So you put AI is one of your subsystem and AO times BI is your other subsystem. And then in this case, entanglement across time represents quantum non-Markovianity. So yeah, there are many ways, and you can make different construction of this type. So there are many ways that you can define entanglement across time depending how you divide your temporal subsystems.
Okay, thank you.
Any other questions?
Yes, ma'am.
Yes, there's one question. Yes, I see a raised hand.
Yes, ma'am. Am I audible?
Yes.
Yes, so in the picture of the changing causal structures because of the presence of yes. Am I audible?
Yes.
Oh yeah.
Yes, can you please repeat your question?
Yeah, in the picture of the changing causal structures because of the presence of a mass, if we assume that we have two subsystems A and B already entangled, and then we are and then the Earth is, and what the mass is actually another entanglement. So if A and B is already entangled, then wouldn't the monogamy of entanglement be violated if we have another Earth entangling with this system?
So A and B are not don't have a prior entanglement. So okay, a more general comment is that monogamy of entanglement will work a little differently in this process that it does with states, although you can still derive some monogamy relations. So in this particular scenario, we are not assuming that A and B are have any prior entanglement between them. So we are just thinking that, yep.
But if in any kind of field theory, we'll have some UV divergences. We will have some UV divergences in the entanglement, right? So it cannot be separable because there will be some correlation function always there.
So maybe the helpful thing is this one. So if you think about a state, then you will have a correlation between or entanglement between your control system, which is the mass, and then a state which represents the connection between A and B. So for example, if you trace out, in this case, if you ignore the mass, if you trace it out, then you will not see any correlation between any entanglement between in the process in itself. So you will have a mixture of A before B and B before A. So that's why I insist that when people talk about superposition of causal order, that's not really correct, because you really need this control system to see that you have a non-classical or an indefinite causal order. So in this case, your observation about monogamy is relevant because, yes, it is true that if you want to, so again, it's a little subtle to talk about entanglement because you have to define exactly what you're saying. But it is true that the fact that you're entangling R with this process subsystems means that when you trace out R, then you don't have quantum correlations in the causal order itself. So in this case, yeah, there is no tension because it's exactly how it works. That the way to detect this indefinite causal order is to perform operations at A, B, and C. So when you make your final measurement at C, you can effectively project into a superposition between A and B or B or A. But if you don't make a final measurement at C, So this final measurement at C is a final measurement of your control system, of the mass. You need to measure the mass at the end of your experiment to prove that your process had an indefinite causal order. If you don't do that measurement, then everything is just completely equivalent to having a random mixture of A before B or B before A.
So the entanglement between A and B is always dependent on the causal order. We cannot just independently say that A and B are entangled.
So again, you have to define entanglement across what subsystems. So for example, if you have entanglement between AI and BI, that is what we usually call entanglement. So that will be an entangled state across the two input systems. If you have entanglement between AO and BI, this means that there is some coherent evolution from the output of one to the input of one. And again, you can, yeah, there will be some monogamy relation, but yeah, if you want to say there is entanglement between A and B, then it will depend on them. So it's not that you cannot have entanglement if you don't have this control. You can have a scenario where you just have, you just prepare an entangled state between A and B without any mass or any other indefinite causal order. It's just in this case, the entanglement will be just some multipartite property of A, B, and C.
Okay. Well, thank you, sir. Answer one more question. Excuse me.
Yes.
Yeah. So one last question here on here we have considered the indefinite causal orders where we have A and I'm not talking about this. I'm not talking about this subsystem. In general, A and B are causally linked to time, and we can take A before B or B before A. But what if we have a scenario in general relativity where that cannot happen? Like for example, if B is in a black hole and A is outside, then in this kind of formalism, how will we represent any kind of entanglement between them?
Yeah, so there have been some works in that direction. I haven't looked in details in that, but yes, in principle, you can do things of that type. So in general, if you have a B inside a black hole, typically that will be in the future of A, in the sense, well, okay, depends what scenarios, but so say that, so you have to think that these are really analogs of events in space and time and not systems that live in space and time. So for example, you can have a word line of an object that falls from outside the black hole to inside the black hole. And then if you define two events along this word line, that will be just two causally ordered events that are not different from any other causally ordered event. Now the scenario that is that would be typical to a black hole is if you start to set around description of multiple events, and then you can describe particularly the causal structure of a black hole, and then you can try to play around. I can put the black hole in a superposition, and so I can put my events in a superposition of being inside and outside of the black hole and things of that type. So all these things are formally possible. I know there are a few studies around there, not too familiar with them, but it's certainly some fun scenario to look at.
But there will be some back reaction from the black hole as well, right? Because if A and B are not similar systems.
What do you mean back reaction?
I mean, like if we have a highly massive body which is causally connected to I mean, it loses mass while going in the black hole, A to B. So A and if suppose some scenario happens like some Penrose process where it loses mass while going in the black hole. So A is massive, B is not, and then if we just interchange the orders, it will have some kind of difference to the structure of the black hole, the controls black hole. So.
Yeah. So I haven't studied that in detail, but yeah, in principle, you can have a scenario. You can include that situations like a black hole evaporation or Hawking. The Penrose process will be a bit easier, I suppose, because they're just extracting energy. But yeah, in this situation, again, you will have to think. So okay, if the question is that the control system can be involved in the operations as well, and the answer is yes. But again, you have to think. You have to understand how to define your events on the control system. So now you can think that your C will be part of this bigger blob, and maybe A, B, and C are only in the blob, and it's not that C is just after. So you can have a situation where the control, you have operations of the control, and the order between these operations is also is possibly indefinite, and it can also affect the order of the other operations. So yeah, in general, you can have all the scenarios. It can obviously become quite complicated.
Okay, thank you, sir.
And there was one last question.
Well,
I don't think there's a further question. Is there any other
hello?
question?
There was
Samgeet, yes.
Oh yeah, yeah. No,
Yeah.
I was just making an observation. Like when you mentioned like the entanglement between the masses, the mass and the process matrix. I guess it's kind of like a genuine entanglement kind of thing, right? Like a GHZ state. Like if you measure the if you make a measurement on the mass, then the other state just loses the entanglement as well. Like
yes, if you make a measurement and you trace out the result, then you lose the entanglement in the other subsystems.
Yeah. So yeah, it just kind of reminded me of the GHZ state. I just want to make that remark. That's all.
Yeah, it's similar. Like the specific form is not that of a GHZ state, but in that sense, it's similar that if you measure one subsystem, then you lose the entanglement between the others.
Okay, yeah.
So, yes, if there are no further questions, I guess I can thank all the audience and a very interesting discussion.
Can I ask a question? So,
I guess so.
yeah. So thank you for your talk. My question is, did you perform channel capacity estimation while considering causal structure?
Yes.
For example, whether channel becomes super additive, sub-additive, or additive.
So we have some work about channel capacity, but I don't have any result in terms of additivity that is different from the long results in quantum communication. So in fact, the results we have are more like in the negative sense, in the sense that if you consider things like channel capacity, then in fact it's not known if indefinite causal structure can give any advantage to definite causal structure. And if you think about simple scenario where you have just consider the capacity from A to B, then you can prove the Olevo bound. So you can prove that the Olevo bound holds even for arbitrary causal structure. What is unknown if you start to calculate combination of capacity, like say you try to calculate the capacity of A to B plus the capacity from B to A, or if you calculate the average capacity or thing of that type, then it's actually not known if there is any advantage. So it's known that there are advantages for other type of communication tasks, but not really in communication capacity defined in an asymptotic setting. And in particular, as concerns the superadditivity, subadditivity, and all kinds of things, essentially you can prove that if you just consider a communication from A to B, then it's not different from using just a causally ordered quantum channel from A to B. So in this case, the indefinite causal order, in fact, just makes noise, but doesn't make any structural difference. But then, yeah, it's an open question. If you have more complicated scenarios and you want to calculate some combined or joint capacity, then that's all open.
Thank you.
Okay, I think that's all. We should break for lunch now. I thank the speaker. Thank you, Dr. Costa.
Thank you. Enjoy your lunch.
Yes. Okay, so we will end this session. Thanks again.
Thank you.
Bye.
Bye.
Thank you thank you all for the participating in this session. This half of our session ends here. Our next session will start from 3 p.m. and we have quite a good talk in this session. So we are expecting the all participant to present in this session in large number. So okay, thank you.